First, I'd like to go over some of the forces being exerted on this hockey stick during a slap shot. This is our ice surface, and to perform a slap shot, we need to make contact with the stick on the ice. In hockey terms, I'm what's referred to as a right-handed shot. This means that my left hand rests here, the top of the stick. And my right hand or my bottom hand is closer to the middle. Normally, hockey sticks are straight when they're in neutral position, but here you can see our stick is curved. My right hand is exerting a force on the stick. And because it's in contact with the ice, this creates enough leverage to create the curvature in the stick. Next, we're going to draw on our puck. Clearly not to scale. Right now, we would say that our puck is at rest. It's not moving, it's sitting in place. Now, when a player is performing a slap shot, there are a lot of other things happening. They have their own biomechanics moving through their body, weight transfer through their legs, the speed that they're moving on the ice. That's a level of detail that we're not going to get into today, but it is important to understand that this is not all that's happening in the grand scope of a slap shot. Now, what's the benefit of taking a slap shot? What's the benefit of curving the stick versus not hitting the ice at all? Or why would we do it? What happens when we make the stick curved like this is that we create what's called a spring potential force. Because the stick's neutral position is straight, we use this force to move it away from neutral. That means when we remove it from contact with the ice, it's going to try and return to its neutral position. So by using our right hand to create a force that bends, we are loading the stick with what we call a spring potential force. Now, this next slide, I've used the green to denote the prior position of the stick. You can see that the stick is rotated along sort of an axis, and that now, while still in contact with the ice, the blade of the stick has now made contact with the puck. All of this energy that we have as potential in the stick is now going to be focused into the puck. As soon as the stick comes off the ice and it returns to its neutral position, it's going to shoot the puck forward at greater speed than if we didn't load the stick. We can use basic tools to determine how much spring potential that this stick has. In professional environments, they use very specific tools, but here we can use 2 clamps, a hook, and some weights, and use the displacement of the stick to determine its spring potential. A spring constant can be thought of as the amount of force it takes to move the stick blade a certain distance. We can determine this pretty easily. All we need to do is secure the stick to the table, use this hook and some masses to weigh down the stick blade, and the ruler to measure how far it travels from its resting position to its weighed down position. Currently, it's hovering right around the 5-inch mark. So now we can use our hook that weighs 1 kilogram and 3 2-kilogram masses for a total of 7 kilograms, which is roughly equal to 70 newtons of force to displace our stick. Now we see that it's hovering right around the 8-inch mark. This tells us that with 70 newtons of force, the stick will bend 3 inches. Before we examine the slap shot, let's take a closer look at the impact force affecting the puck without any loaded spring potential. So here we see, we've got the black puck stacked on top of the blue, on top of the green, just to give us a little bit of height to ensure that we can hit the puck without hitting the ground first. And what we see is that the green puck stays in place, and that the black and blue pucks are moving at different speeds. This has a lot to do with the fact that they're different weights. They've been hit with the same amount of force, but because they weigh different things, they're going to travel at different speeds. Now we can use a relationship of the impact force to determine the amount of energy that is transferred to the puck. And this is called kinetic energy. we're specifically going to refer to this as the kinetic energy of the impact. The relationship of energy to the puck is from its mass times its velocity, or speed, squared. So if we want to determine the amount of energy in the puck while it's moving through the air, it's as simple as 1/2 times its mass, 0.166 kilograms, or 166 grams, times its speed, (22.7 meters per second) squared. If we were to run this calculation, we'd see that the puck has 42.8 joules of energy. And what that just is telling us is that from just hitting the puck by itself with no extra loaded energy, that's the amount that can be transferred into it. Now let's take a look at the slap shot and we'll see something very different. So here we can see we still have that same relationship, the kinetic energy, this time from the slap shot. But we have a new relationship. It's called the spring potential of the shot. Now this is related from our spring constant, which we talked about earlier. We're going to use an average from a study from Penn State showing that the average spring potential of a stick of my flex rating is 8,931 newtons per meter. Now, one of the laws of energy conservation tells us that when we have potential energy, virtually all of it is transferred to kinetic energy. So that means when we start with P initial is equal to K final. And that all of this is going to get used up to transfer into the puck and put it in motion. So now, let's determine the amount of spring potential energy we have from loading the stick. We can find this value by measuring the distance from where the stick's neutral position would be to its distance of deflection. So you can see in the video that as I'm taking this shot, the stick is actively bending. And because it's bending this far, we plug it in, find 1/2 times our spring constant times the distance, so 0.25 meters squared. So if we just run a calculation there, we're going to find that by doing the spring-loaded slap shot, the amount of potential energy we're going to transfer into the puck has gone up by 7 times what it was before. We saw earlier that from just hitting the puck, that was only 48 joules of energy. So we can assume that if we're starting with this much more, the puck is going to be moving much faster. That agrees with what our eyes are telling us. So now, let's use our relationship that all of this potential energy can be converted into this amount of kinetic energy. So we start 279.1 joules of energy. Now this is equal to 1/2 times the mass of the puck times its velocity squared. Now we'll plug in these numbers. So to find the speed of the puck from this relationship, we'll just use some algebra to rearrange and solve for V. And that value shows that the puck is moving at this moment with a speed of 58 meters per second. So here we see that we've almost tripled the speed of the puck and used a greater amount of energy. This shows us that there's a higher level of efficiency to using the slap shot. You load the stick with the spring potential energy, and you can translate that into a faster moving puck and have a better opportunity to score a goal. And with that, my last piece, clean up your lab station. See, it ain't that hard.